In the last video, we looked at friction and where we see it in our everyday life. What we are going to do now is look at the basic formula for frictional force, and then we will modify it slightly to accommodate our class. We see that the frictional force is equal to mu multiplied by the normal force. In this case, mu is a coefficient that is unique to each type of surface. Mu does not have any units. Looking at this picture, the frictional force pointing in the opposite direction the sleigh is traveling is equal to mu multiplied by the normal force between the ground and the sleigh, which points up. In our class, we will only have steady motion in these types of problems, so we don't have to worry about any acceleration. That simplifies our formula because when we have zero acceleration, we also have zero net force acting on the object, and we can replace the frictional force with the pulling force, which is equal to mu multiplied by the normal force. In this picture, we can see that with steady motion, the friction force arrow is the same length, but in the opposite direction as the pulling force arrow. Since these arrows are the same length, they represent the same force being applied. One last modification to our formula. In this class, we will only have motion on level ground, which means that the normal force is equal to the weight force, or the weight of the object. Again, since the weight force is equal to the normal force, the lengths of those arrows in the picture should be exactly the same. This brings us to the final version of the friction formula we will be using in our class. Pulling force is equal to mu multiplied by weight. Looking at the equation circle, we see that we have pulling force on top with mu and weight on the bottom. Just like in the last section, we also have unit circles for our units. In the English system, pulling force and weight are both measured in pounds. Mu does not have any unit since it is simply a coefficient or just a number. In the metric or SI system, pulling force and weight are both measured in newtons, abbreviated with an N. If you are unsure of what your units should be in your answer, look back at these unit circles. In your notes, you see this table. This table gives us some common values for mu. Notice that we have a starting friction and a sliding friction column. You will need to read each question carefully and then decide if the problem is looking at an object that is initially at rest, where you will use starting friction value for mu, or if the object is already sliding and you need to keep it moving, where you will use the sliding friction value for mu. Like I mentioned before, the starting friction value is always larger than the sliding friction value, except for lubricated steel on steel. Since it is lubricated, the starting friction and sliding friction are essentially the same. Let's take a look at a couple of examples. A pulling force of 170 newtons is needed to keep a 530 newton cardboard box sliding on a wooden floor. What is the coefficient of friction? First of all, we need to figure out what we are solving for and look at the equation circle to come up with a formula. In this problem, we need to find the coefficient of friction, which is mu. Covering up mu on the equation circle, we see that it is equal to pulling force divided by the weight. Our pulling force is 170 newtons, and the weight force is 530 newtons. Dividing 170 by 530 newtons, we see that we get a value for mu of 0.32. Remember, mu is a unitless coefficient, so do not include units. Now we need to decide if this is starting or sliding friction. Since the problem asks the force needed to keep the box sliding, this would be sliding friction. Let's look at one last example. A hardwood crate weighs 780 pounds. What force is needed to keep the crate sliding on a hardwood floor? In this problem, we need to find the force needed to start the crate sliding. In other words, we need to find the pulling force. Covering up that in our equation circle, we see that our formula for pulling force is mu multiplied by weight. Now we need to refer back to our table to find a value for mu. Since we are looking at starting the crate sliding, we need to use the starting friction value. The materials we have are hardwood on hardwood, so our value for mu is 0.40. Now we can substitute that in for mu, and the weight is 780 pounds. Multiplying, we see that our answer must be 312 pounds. This concludes our discussion on frictional forces.